When you use the word ANOVA to describe a linear regression model, one norm, perhaps the key norm, is that you will find a way to present main effects in addition to all the details of regression interactions that we covered previously. And that's not as easy as it sounds, so this part of the video is going to cover how to do that. But remember, it's still nothing special about ANOVA. It's just regression by another name, and you can do all of this main effect stuff even when you're not choosing to use that name. There are various options for defining main effects, and that's why this part gets pretty technical. But I'm doing it because inconsistencies between software packages and definitions of main effects are a common source of confusion for students who use or try more than one statistical program. I will now spend some time on the distinctions between the various options for defining main effects. You should know that these distinctions are not all that important in practice most of the time. At the end, I will tell you about a perfectly good default approach that you can generally stick with. So, several types of main effects. I have a written description of this concept on my website. The link is in the description. And if you watch this video, you'll get the same conceptual material as that written description. But the description might be a good way to revisit this material later on if you forget. Suppose you have an interaction between two binary variables. If you pick one of those variables, you should recognize that its association with the response variable can be described by two conditional associations, one at each value of the moderating variable, the other variable in the interaction. Those two conditional associations are often termed simple effects. We want a way to get an overall main effect for this variable instead of two separate simple effects. Here are the three main options for defining an overall main effect in this situation. One, you can take the midpoint of the two simple effects. This approach ignores the sample sizes in each group entirely and just defines the main effect as the point right between them. Two, you can estimate the effect at a point that is closer to the larger group. This is like a simple effect weighted by the sample size, closer to the larger group of the moderating variable. It takes into account some information about sample sizes, but it ignores differences in sample sizes between the groups of the variable you're focusing on. If that's confusing, don't worry, I'll come back to this idea. The third option is to fit a least squares regression model without the interaction term at all. This approach takes into account all four sample sizes. This kind of main effect can be interpreted in the same way as any other slope from a regression model with multiple predictors. It can also be thought of as a best guess of the effect of x, given the provisional constraint that the effect must be the same in both conditions of the moderating variable. Any of these three main effects can be used for ANOVA, but people don't usually specify which one they mean, and that's what can make the terminology confusing. How do we actually get main effects estimated between the conditional effects? When we explore an interaction the conventional way, we change the reference categories of the predictors to get conditional associations at key values. For example, if you have a coffee condition and a decaf condition, you might encode coffee as 1 and decaf as 0, then decaf is the reference point. You might swap it so that coffee is 0 and decaf is 1, and at that point, coffee is the reference point. The same strategy allows us to use reference points that fall between the categories. For example, if you encoded coffee as -1 and decaf as +1, the reference point would be right in the middle, right between them, because 0 falls right between -1 and 1. If you encoded coffee as +3 and decaf as -1, then the reference point would be 1/4 of the way from decaf toward coffee. It would be closer to decaf than coffee because 0 is closer to -1 than it is to +3. Let's try it in R. Here we are at an R console. I'm going to walk through some example data sets. I have a link to the code and the example data sets in the description of this video. And the first thing that I've done is load the car package, CAR, which is going to be vital to the types of F-tests that we want to run later on. The first example data set that I'm going to work with is this dog example. The premise of this example is that 300 dogs ran through an obstacle course, and the researchers recorded 3 things about them: whether the dog had spots or not, whether its fur was curly or straight, and the number of seconds it took for it to get through the obstacle course. So spots is recorded as an integer with values 0 and 1, 1 being spots, 0 meaning no spots, which should be perfectly fine for including this binary variable in a regression model. Fur is here a factor that has 2 levels, curly and straight, also perfectly fine for including in a regression model because R will automatically encode this factor with an indicator variable where one of the levels is 0 and the other is coded as 1. And seconds is just recorded as a number, so it will work fine as the response variable in a regression model. I'm showing here a table of the output of the complete cases function on the entire dataset zoom, which came from zoom.csv, just to illustrate to you that all 300 rows in the dataset are complete observations. There's no missing data. So if there was missing data, some of the things that I'm going to do might require additional consideration. The first thing that we should remember how to do with a dataset like this is characterize the interaction. So the idea is that we're going to use the fur type and spots variables to predict the number of seconds it took the dog to run through the obstacle course. So I will specify that I want the reference category for the fur variable to be curly, and then fit this regression model, which is the same as last week, the LM function with the response variable, a tilde, and the predictor variable separated by an asterisk rather than a plus sign to indicate that we want an interaction between them. And I'm plugging the result of this LM function call directly into summary because all I want for now is the summary table. But you could also store it as an object of its own right and plug that object in as the first argument to summary. This output illustrates that there is a statistically significant interaction between the presence or absence of spots and the straight or curly nature of the dog's fur. The interaction p-value is 5 times 10 to the negative fifth, which is very low, so we'll call that statistically significant. And this means that the relationship between spots and time on the obstacle course depends on whether the dog has straight or curly fur, and it also means that the relationship between fur type and time on the obstacle course depends on whether the dog has spots or not. Let's focus, for example, on the spots variable. The slope here is negative 23.63, and that indicates that the dogs with spots ran the obstacle course 23.6 seconds faster than the dogs without spots when their fur was curly. Recall that the interpretation of this slope depends on the reference category of the moderating variable because there is an interaction in this regression model. The reference category for fur is curly because the indicator variable that was included in this model had straight coded as 1 and therefore curly coded as 0. So this is the conditional association between spots and time on the obstacle course for the curly-haired dogs. Of course, I would also like to know the conditional association between spots and time on the obstacle course for the straight-haired dogs. So I used the relevel function to specify that I now want the reference category for fur to be straight. I've replaced the fur variable in the Zoom dataset with this slightly modified version, and I fit the exact same regression model again. And here we can see that the slope for the spots variable is negative 12.6 rather than negative 23.6 like it was before. This illustrates that the dogs with spots still run faster, but when their hair is straight, they only run 12.6 seconds faster than their counterparts without spots, whereas the curly-haired dogs showed a bigger differential between those with spots and those without spots. We can also interpret the other conditional slope in this regression model. The fur curly slope is negative 0.5 seconds, which indicates that the curly-furred dogs ran the obstacle course half a second faster than the straight-furred dogs among those who had no spots, and that difference is not large enough to be statistically significant. If we wanted an estimate of the difference between the curly and straight fur in the case where the dogs have spots, then we would need to alter the encoding of this spots binary variable so that spots is 0 and no spots is 1. In this case, spots is not a factor, it's just numbers 0 and 1 in the first place. So I can create an alternative version of it called no spots that is just the result of 1 minus zoom $spots, the spots vector from the zoom data frame. And this will result in a new vector that has 0 for those who had spots and 1 for those dogs that did not have spots. Then when I run the regression model with no spots instead of spots as the indicator variable, I see that the slope for fur curly is different. There was almost no difference between curly and straight-furred dogs in the case where they had no spots. But when they have spots, when spots is the reference category, the dogs with curly fur run the obstacle course 11.5 seconds faster than those with straight fur, and that difference is statistically significant. This is another way of thinking about what this interaction means, and for the sake of completeness, I wanted to show it to you to remind you of what was covered in the last video. So when we looked at these summary tables and we noticed that the conditional association between spots and seconds on the obstacle course was negative 23.6 for the curly-furred dogs and only negative 12.6 for the straight-furred dogs, we learned something about the nature of the statistical interaction that is present in this model. But if we're reporting these results using the communication norms typical of ANOVA, then we will also want an overall main effect for spots. In other words, we will want to be able to characterize for the audience what the typical differential is between spots and no spots, regardless of whether the fur is straight or curly. And that means we need some kind of an association between spots and time that lies in between negative 12.6 and negative 23.6 to call the main effect